Go ahead.
Okay, cool. Hi, everyone. So my name's Guy. I'm a master's student at the University of Cape Town under Giovanni, Casini, and Meyer. So today I'm talking about Boolean KLM, which is a logic we looked at for diffeasible reasoning. So it's an extension of what's known as the KLM system, which we've just seen in Clayton's talk. And I'll talk a bit more about that. Since we don't have too much time, I thought what I'd do is go over some of the background that's relevant for this paper, and then run through what we looked at in the paper and some of the results we had. Oh dear. Why can't I change the? Ah, there we go. Okay, so I thought a good place to start would be, well, in order to talk about feasible reasoning, we should first understand what classical reasoning is. And I think this is a kind of reasoning that's familiar to everyone here. It's reasoning according to the laws of classical logics, like propositional logic or first order logic. And it's a kind of reasoning you'll be familiar with from mathematics or philosophy. So a really simple example of this is, suppose we have a premise, penguins are birds, and I'll use bird examples because the NMR community is fascinated with them, as am I. Birds are animals, that's a second premise. And from these premises, we can conclude, well, penguins are animals. And this argument is classically valid because whenever the premises are true, the conclusion is true as well. And classical logic is very useful in a lot of contexts. And it satisfies some nice properties, like quite a famous property, monotonicity. So monotonicity says that if you add premises to a valid argument, it doesn't invalidate the conclusion. So in this case, we can add a premise, like, for instance, penguins eat fish, and it doesn't change the fact that penguins are animals. Our conclusion is completely unchanged. And this is a very, very important property of classical reasoning. For instance, in mathematics, it would be extremely inconvenient if we had to throw away large parts of mathematics every time we proved a new result. The fact that we can rely on monotonicity is very useful in that context. And as I've said, it has to do with the fact that adding new premises is not invalidated our conclusions. However, in other contexts, it's actually not that desirable. So this is where defeasible reasoning comes in. It's all about reasoning in which premises, new premises, or in other words, learning new information, can invalidate previous conclusions. So for instance, if you're working with approximate or incomplete knowledge, or as we've seen in Clayton's talk, even humans reason like this, having monotonicity is not a desirable property of your model or formal system. So let's go through like another example. Premise one, the same premise. Suppose we know that penguins are birds, and suppose we know that birds can fly. If this is all we knew about penguins and birds, it's quite reasonable to conclude that penguins can fly. After all, this is what we'd expect from the information we have. And if you don't think this is a reasonable argument because you know, for instance, penguins don't fly, well, replace the word penguin with something else, like ogle-boggle or whatever you like. The point is that given incomplete knowledge, this is a reasonable conclusion. However, if we were to learn a new fact about penguins, so for instance, penguins are too heavy to lift themselves with their wings, well, suddenly our conclusion isn't so reasonable anymore. And this is what feasible reasoning is all about. It's about reasoning without monotonicity. And another interesting thing about feasible reasoning is that unlike classical logic, where what is meant by classically valid arguments and classical reasoning is quite pinned down, there are a lot of different ways you can do defeasible reasoning, depending on the context. And different systems might work better in different contexts. So in the last talk, for instance, we saw that perhaps KLM-style defeasible reasoning isn't that accurate for modeling human reasoning, but it might be a better fit for other contexts. Right, so what is a KLM framework? Because that's sort of the starting point for our paper. Well, the KLM framework's an axiomatic formal approach to defeasible reasoning. So it's an approach using formal logics to model the defeasible reasoning systems. It was introduced by Krauss, Lemon, and Magador in the 90s, and that's where the acronym KLM comes from. So how does it work? Well, their approach is to take a base logic, such as propositional logic, with all of its standard connectives, such as implication, conjunction, disjunction, and we add in a new connective, this twiddle symbol. And this twiddle symbol represents a defeasible implication. So for instance, alpha twiddle beta intuitively is supposed to mean that beta typically or defeasibly follows from alpha, but it might not if we learn more information. For instance, it might not if we come across new information and validates the conclusion. And different systems for defeasible reasoning, or different ways of approaching defeasible reasoning, you can talk about in the KLM framework by providing different semantics for this twiddle symbol. So different semantics gives you different feasible consequence relations, different models of feasible reasoning. So how in the KLM framework are these formulas given truth values? So how do we interpret them? And the way this works is you take every propositional valuation or possible world, and I'll explain what I mean by that shortly in case it's unfamiliar to you. So here's an example of a ranking where you see, so P stands for the property of being a penguin, B for being a bird, and F for flying. So a string of symbols like PBF means a possible world in which being a penguin is true, being a bird's true, and flying is true. Possible worlds or valuations that have a lower rank are considered more typical. So the rank 2 world there, PBF, that's considered extremely atypical. And in line with our previous example, this is because it's a world in which penguins fly, which we expect shouldn't hold. And then the rank 0 valuations or possible worlds are the most typical worlds. So the way we can assign truth values to defeasible formulas in the KLM framework is as follows. So suppose we're interested in whether penguins typically don't fly, which is what this defeasible formula says. So in order to tell whether it's true, we take our ranking and we look at all the valuations that satisfy P, and there are 2 of them highlighted here. And we say, right, in the most typical of these valuations, which is just this single valuation highlighted, does not F hold? And in the ranking, the overbar means negation. So in this world, indeed, flying does not hold. And so in this rank's interpretation, it satisfies penguins typically don't fly. And of course, there are other rank's interpretations that satisfy this formula as well. This is just an arbitrary choice. Right. And one of the results in the original KLM papers is that these ranked interpretations, so different choices of these ranking functions, can completely characterize a large class of defeasible consequence relations. So many different kinds of defeasible reasoning can be characterized in this system. And there are a number of properties that these defeasible relations satisfy. They were shown briefly in Clayton's talk, but I won't dwell on them because it's not important for this one. Right, so what's the problem we tackled in our paper? Well, the vanilla KLM-style conditionals are not very expressive syntactically. And what I mean by this is you can express things like this green formula, alpha typically implies beta, but you can't express things like alpha typically doesn't imply beta. You can't express conjunctions and disjunctions of defeasible knowledge, and you can't nest defeasible knowledge. So there's some limitations to what you can actually express using this framework logically. Some people have worked on extensions of the original KLM framework that deal with some of these problems. So Richard Booth and Hilton Paris, I think, in the late 90s, they considered an extension with negative conditionals. So you can express things like beta typically doesn't follow from alpha or defeasibly doesn't follow from alpha. And more recently, my supervisor, Giovanni Casini, and co-authors introduced another logic, propositional typicality logic, which is much more expressive logic for representing defeasible knowledge and reasoning about it. So what we did is we took the work of Richard Booth one step further, and we said, right, in Boolean KLM, which is the logic we studied, we're going to allow arbitrary Boolean combinations of defeasible knowledge. So you can have negations, conjunctions, disjunctions, the works. One thing we didn't allow is nesting, because that complicates semantics a bit, but perhaps we could look at that at a future date. And the question we were interested in is how much of the theory for vanilla KLM still holds in this expanded framework. So there are, for instance, very nice or mathematically nice ways of defining feasible entailment in the original KLM framework via rational closure or lexicographic closure or relevant closure, a number of different ways to do this that are quite well known in the NMR community. And we're wondering, can we still do this for Boolean KLM? So what are our results? First of all, we showed that Boolean KLM formulas can characterize any subset of ranked interpretations. Or in other words, as far as representing the feasible consequence relations goes, Boolean KLM is about as expressive as it can get, or as you can get, which was surprising to us because propositional typicality logic seems to be more expressive than any kind of KLM framework. The fact that Boolean KLM is as expressive as possible means that there should be a way to translate formulas from previous extensions of the KLM framework into this new extension. And so one of the things we do is we provide explicit translations from, for instance, propositional typicality logic into equivalent BKLM formulas. And finally, we investigate whether entailment relations like rational closure and its related families can be defined for Boolean KLM knowledge bases. And we show a number of impossibility results that prove that actually a lot of the nice properties you get in the original KLM framework don't hold in this expanded framework. So there are some strong restrictions that we sort of mark out about what you can do as far as feasible entailment goes in this expressive logic. Which I think brings us to 12 minutes. And that's all I have for you today. Thank you. Any questions? I see a question from Ivan. How does your framework compare to Craig Boutilier's conditional logics of normality, in which I think all the Boolean combinations you're interested in here can be expressed? I must admit, I'm not actually familiar with that paper. I do know that a number of papers have considered Boolean combinations of these KLM-style conditionals in the past. But as far as I know, the problem of defining entailment relations and what kinds of properties you can expect in these entailment relations hadn't been studied before. Perhaps Craig's paper does say something about that. I'm not sure.
Perhaps I can make a remark about this as well.
Mm.
So Craig Boutilier's logic that he introduced in '94 is much more expressive than what we're looking at. In our view, much too expressive. So yeah.